Now we
uh,
uh, continue to study
three,
lecture 3,
part one.
part 1.
Okay.
Okay,
We
we
discuss
to discuss about
cross product.
cross product.
Of course, we
Of
know, right?
course, we know, right?
We have
We
A
have
cross
A
B.
cross B.
Okay.
Okay,
A cross
A
B.
cross
So we
B. So we
consider the phase
consider the
angle
phase angle
from A
from
to
A
B.
to B.
Or we can
Or we
apply
can
right
apply
hand rule,
right hand
right?
rule,
We
right?
can
We
get
can
the
get
resultant
the
vector.
resultant vectors.
Okay.
Okay,
Yeah, is a
is
upward
upward
direction.
direction.
Otherwise,
Otherwise,
if we
if we
consider B
consider B
cross A,
cross
right?
A, right?
B cross A,
B cross
so
A,
from
so
vector
from
B
vector B
comes to
comes
vector A,
to vector
so
A,
resultant
so
vector is
resultant vector is
downward
downward
direction. Okay?
direction.
Yeah.
Okay, yeah.
So
So
if
we
we have
have vector
vector
A and
A
vector
and
B, this
vector B,
one, and we have the surface,
we have
right?
the
We have
surface,
the surface,
or we have the
or we have
area
the area
to
to
contain
contain
vector A.
vector A and vector B.
Okay, we
Okay,
say
we
the
say
surface.
the surface.
Okay, yeah.
Okay,
And
and we
the
have
resultant
the
vectors
resultant
will be
vectors will be
perpendicular to the
perpendicular
surface.
to the surface.
Okay, what is
Okay,
this? This
what is
one we
this? This
say
one we
vector
say
space.
vector space.
Vector space.
Vector space.
Okay,
Okay,
the
yeah.
vector
The
space
vector
will
space
contain
will contain
vector A and
vector A and vector B.
Okay, which is vector
Okay,
space.
which is vector space.
Oh,
Oh,
now we
now
have
we
the
have the
definition of
definition of
gross product.
gross product.
Okay,
Okay, we
we have
have
R3, right?
R3,
We have
right? We have
three
three
dimension,
dimension,
right?
right?
Three-dimensional space
Three-dimensional
R3.
space R3.
Okay, why?
Okay, why? Because
Every
every
vector
vectors we have
three elements,
three elements:
U1,
U1, U2, V2,
and vector V
and
we
vector
have
V we
V1,
have
V2,
V1,
V3.
V2, V3.
Okay, yeah, we
Okay,
take three
yeah, we say
dimensional space.
three-dimensional space.
Yeah,
Yeah,
and
and we can get
cross
the
product,
cross
U
product
cross V.
U cross V.
Okay, so here
Okay, so
like
here
I
like
overhead,
I
J
overhead,
overhead.
J overhead, K
Okay,
overhead. Okay,
so when we
so
cover
when
this
we
one,
cover
you
this
get
one, you
U2
get
times
U2
V,
times V,
3 is minus,
3 is
U3
minus,
V2,
U3 to V2,
and blah blah blah
and
blah.
blah blah blah
Okay,
blah.
and
Okay,
then when we
and then when we
consider this one,
consider
you
this
get
one, you get
U3 V1
U3
minus
V1
U1
minus
V3.
U1 V3.
And when we cover
And
this
when we
one, you
cover
get
this one, you get
U1
U1
V2 minus
V2
U2
minus
V1.
U2 V1.
Okay, yeah.
Okay, yeah.
So we can get
So we can get the results of
the gross
the
product.
gross product.
Okay, and this one.
Okay, and this one is example. Okay,
So we have
so
vector
we have
U
vector
cross
U
vector V.
cross vector V.
Okay, A is what?
Okay, A is
1,
what? 1,
2 minus
2
2,
minus 2,
3, 0,
3,
1.
0,
Right?
1. Right?
Right.
Right.
So this is I
So this
alpha.
is I overhead, J overhead, K overhead because we have three
So
dimensions.
you get
So
2
you
times
get 2
1
times
minus
1
0.
minus 0, you get 2.
Right?
Right?
And then
And then when we
you
consider
get
this one, you get
minus 2
minus
is
2
minus
times 3 is
6
minus 6,
1
minus 1, you get minus 7.
Okay?
Okay?
And when we
And when we
consider
consider the last one, you get 1 times 0 minus 2
you
times
get
3,
minus
you
6.
get minus
Okay?
6.
So we
Okay?
can get
So we can get
the
resultant vectors.
Okay?
Okay? We also have some properties in relation to the cross product of vectors. Okay?
Yeah.
Yeah.
So,
Look,
we
we have U cross V.
okay, U
Okay, U cross V is orthogonal to U.
We say
We say orthogonal or we say it's perpendicular. Okay.
Then
And then when we take the dot product,
you get 0.
you get 0 because
They are perpendicular.
they are perpendicular to each other.
Okay.
Okay. And similarly, this one you get 0.
Okay. The
Okay.
norm.
The norm.
Okay.
Okay.
Norm
Norm
of U cross V.
U cross V, U cross V, and we took
Power up to.
power up 2.
Okay.
So we can get the norm of U square, the norm of V square minus U dot V totally square.
Okay. Anyway.
Okay. Anyway, this one you
can understand.
can understand. Yeah.
And then
here we have U cross V plus W
is equal
to U cross V plus U cross W. You need to consider the sequence,
the sequence
the sequence or the order.
U cross V
U cross V plus U cross W.
and this one
We have U cross W plus V cross W. Okay, remember the sequence. If you make a reverse sequence, you get different result because this is cross product. Okay. He's listening very well. Okay.
So
if U cross zero vectors is equal to zero, vector cross U is equal to zero, of course. Okay.
and the
U cross U is zero.
Yeah.
Yeah.
We also
understand this one, right? From physics 1, we discussed about this one. Okay.
And
we need to follow the sequence. Okay, I to J, right? J to K, and then K come back to I. Okay. Yeah. So we can calculate the norm of U cross V. Of course, U cross V,
you can get
resultant vectors, maybe vector C.
So
Okay. So when we take the norm of vector C, that means the norm of U cross V, right?
So
the norm of U cross V is the norm of U, the norm of V, and sine theta. Theta is the phase angle between vector U and vector V. Okay.
Yeah.
Yeah.
So
starting with this one, this equation.
we
Okay. We know for U dot V is the norm of U, the norm of V, and cosine theta.
Okay. And
Okay.
then
you replace to here, right? To here,
get
you can get the norm of U cross V square is this one minus. This is square, right? This is square. You get this one is square.
So we can get
the norm of U square, the norm of V square, cosine square theta.
So
Okay,
that
that means we take here this is the common variables here, and inside the bracket we have 1 minus cosine square theta. This one minus this one is sine theta square.
Okay.
Okay.
So
And then we take this square root of both sides. You can get this one. We demonstrate the norm of U cross V is the norm of U times the norm of V times sine theta.
Okay.
Okay.
So if we have
U
dot V,
we have U dot V,
the norm
you can get
U,
the norm of U,
and
the norm of V, and cosine theta.
right?
Cosine
And
theta. And if we have the norm of U cross V, you can get the norm of U, the norm of V, sine theta. Okay. Yeah.
Here we
mention about the areas of a parallelogram. Okay.
We have
vector U and vector V in three space. Three space, that means R3. We have vector U is U1, U2, and U3. Okay, three dimensions. That means every vector will have three variables, right? Or three elements.
We have vector V,
we have V1, V2, and V3.
Okay. Yeah.
Okay. Yeah.
Then
the norm of U cross V is equal to the area of the parallelogram determined by U and V here.
Okay.
For example, here we have vector U.
Here we have vector V.
Here we have vector V.
Okay.
So when we take the norm of U cross V, you can get these areas. These areas. Okay.
And divided
by
divided
by 2. Okay, you get this one.
I mean this one.
This area. Okay.
Yeah. So if we would
like to calculate the triangulars, we consider this one. Otherwise, if we consider the norm of u cross v, you get this area, the area of rectangular.
Right?
Okay. Of course, this one is
maybe
it's
90 degrees.
90 degrees. Okay, it's 90 degrees
because
we apply parallel.
Okay, to look for
find the areas of the triangle determine blah blah blah. Okay, so like this one is vector u, this is vector v.
Okay, you can get
this area.
Or if we
just consider the norm of u cross v, this is the areas of parallel. Okay.
So here is
the definition for
scalar
triple
product.
Okay. Yeah.
We have
u dot v cross w.
Okay.
So v cross w.
You can get this one, right?
Get this one, right? This one.
And then
u dot. So you get one more
a row
at the top. Okay.
Remember
v cross w,
and we
have v1, v2, v3, w we have w1, w2, w3. When we take v cross w, you get v1, v2, v3, w1, w2, w3. Now we times u dot, right? U dot.
So you can get
u1, u2, u3 here. Okay. Yeah. So this one like determinant, right? Determinant.
Because
if we consider this row, this rows and this column, you get a u1. So u1 times v2, v3, w2, w. This is determinant, right? And if when we consider the second column in the first row, we have minus u2, blah blah blah. And the first row and the third column, you get u3. So this one like determinant, right? Determinant. Yeah.
So if here
is the determinant, you can guess the result.
That will be
a scalar number. So that's the reason we say a scalar triple product.
Okay.
Right?
Yeah.
Example.
We have
u dot v cross w, right? So here we have u1, u2, u3, right? And v cross w, you get v1, v2, v3, the second row. And the last row we have v, w1, w2, and w3. Okay? So we can get what? U we get 3 minus 2 minus 5.
And v we
have 1, 4, minus 4. And w we have 0, 3, 2. Right? This is determinant, right? When we calculate determinant, we have 3, right? 3. And then we have C11, right? Right?
This is for
example here A11, A12, A13. So you get A11 times C11, right? Plus A12, C12, plus A13, C13. You remember?
Yeah.
Okay, and then you can get 3, and here this is 1, 1. So minus 1 to the power of 1 plus 1, you get 1. So you get here 4, 3, minus 4, 2. And then A12, you get minus 2, right? Minus 2. And then minus 1 to the power of 1 plus 2, you get minus, you get positive, right? And then here you can get what? 1, 0, minus 4, 2, right?
And then blah
blah. Okay, and then you get minus 5 and minus 1 to the power of 1 plus 4, you get 1. And then you can get 1, 0, 4, 3.
Okay?
Times. Okay.
Then we can
get how many?
A
minus you get 20. 20 times 3 you get 60.
This one is
This
2
one is 2 times 2 you get 4.
This one is
This one is 3. 3
5
times minus 5 you get minus 15 you get 49. So
The answer is
the answer is
49.
49.
Okay, so this one
So this one we say a scalar
triple product.
triple product.
Okay? Yeah.
Okay? Yeah.
Okay, this one for
Okay, this one for your we finish lecture
3
part 1. Okay.
Yeah.
To your homework.
We have no homework.
No homework.
Of lecture 3.
3 part 1. Okay.
And this one just
This one just exercise. That means you practice
for yourself.
Okay.
Okay, so
for
homework
the homework of lecture 3 part 1.
Now we
go to lecture 3 part 2.
Okay, and
we hope we can finish lecture 3 part 2
today.
we hope.
Yeah,
maybe I will skip some session. Okay, and so lecture 3 part 2 is very important. Okay.
Yeah.
It always appears in the final exam.
Okay.
So please
take into account
lecture 3 part 2.
Yeah,
we study some definition of spaces and subspaces. Okay. We study 4 fundamental subspaces. Okay. What is a spanning set and linear independence. Okay.
And this one for
lecture 3 part 2, and this one for lecture 3 part 3. Okay.
So
here we have a definition of a vector space.
Okay.
Let V be a set on with 2 operations, vector addition and a scalar multiplication, undefined. If the list axioms are satisfied for every vector V and vector W in V, and every scalar a positive number C and D, and then V is a vector space. Okay.
Me too. I don't understand
too. Okay.
So
to understand what is vector space.
Vector
space means a space,
right?
To contain all vectors. Say vector space. Okay.
Yeah.
So we have vector space V to contain how many vectors? For example, we have vector U, vector V, and vector W.
Okay. So
we say V is a vector space if all axioms here
are satisfied.
So if we have U plus vector V must be
in
the vector space.
And then
U plus V
must be
equal to V plus U. Okay.
And then
axiom 3, 4, 5, 6, 7, 8, 9, 10. Okay. So the first one we say closure under addition, and the second one is commutative properties, blah 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 blah. Okay. But if we consider the first 5 properties, this one is addition, right? Addition, right?
Okay.
So we say vector addition.
And
the other 5 properties we say scalar multiplication. Right? Because C times V, C times vector U or C times U plus V
is equal to C
times U plus C times
okay.
So in general, we can say we have 2 properties, two general properties, vector addition and vector scalar and scalar multiplication.
Okay.
So
normally
we don't need to demonstrate all properties here. We just focus on number 1 and number 6.
Okay.
Okay. So if number 1 and number 6 are satisfied, normally the others will be satisfied. Normally, not always. Okay. So to demonstrate V
to be a
vector space or not, we just double check with SM1 and SM6.
Okay.
Okay.
Maybe we have
example and then you can understand.
So
example.
Here.
Not example. Here, just some steps. Okay. Look. To demonstrate the vector space. Okay. To identify the vector space. Step 1. Identify the set V of objects that will become vectors. Identify the addition and scalar multiplication operation. Verify SM1 and 6. SM1 we say closures under addition, and SM6 we say closure under scalar multiplication like this. Okay, like this. Closures under addition and closures under scalar multiplication.
Okay.
Okay. Yeah.
And then confirm that
SM2, 3, 4, 5, 7, 9, 8, 9, 10, so on.
Okay, but normally
we can skip step 4.
Okay,
not always, but normally. Now
we have
zero vector space.
Why we have
zero vector space? Because we need to demonstrate. We need to demonstrate all assumes will be satisfied. That means SM1 we have what? We have vector U plus vector V belong to what? Belong to V.
Right?
And C times vector U belong to V. Right? And vector space V contains many zero vectors.
Because this one we say
zero vector space.
Vector
zero space means a space to contain all zero vectors.
Okay. So
if I say vector U is 0, vector V is 0, so 0 plus 0, you get 0 vector. So we satisfy SM1.
Okay.
And then because this is 0, belong to vector 0 vector space. And then we have SM6. We have C times U is C times 0 vector. C times 0 vector is 0 vector belong to 0 vector space. So we say vectors we say V is a 0 vector space. Or we have 0 vector space.
Do you understand?
Continue. Now we have Rn. Rn is a vector space. What's the Rn? Rn is a set of all vectors with how many dimensions? N dimensions. So that means we have vector U, we have U1, U2, blah 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 2, Un. We have vector V, we have V1, V2, blah blah blah, Vn. And we have many vectors. For example, vector Z, we have Z1, Z2, blah blah blah. How many vectors are vector space? I don't know. But I know a vector space Rn is a space to contain all vectors with
an
element for every vector.
Do you
understand? Yeah. Okay. So we have vector space is Rn, a set of all vectors with n elements for every vector. So if we say vector U is U1 blah 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 Un and V is blah blah V1 V2 blah blah Vn. So if we have U plus V, that means you get U1 plus V1, U2 plus V2 blah blah Un plus Vn. So how many elements we have? Also n element, right? So this one belongs to vector space is Rn. Okay. Yes. Then we have scalar number times U. You have U1, U2, blah, blah, Un. And then we K times U. That means K times U1, K times U2, blah, K times Un. This one belongs to Rn.
Right?
We don't care about the values. But I know this one is real number. right?
Real numbers.
Real numbers. For example, if we have vector u, we have 1, 2, blah, 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 10.
Okay.
And then we have k times u. For example, k is 2. This is scalar number.
So you get
2, you get 2, 4, blah, blah, to 20s. Okay?
This is real number.
This is real number.
You remember?
And then how many elements? N elements.
Okay,
so we conclude that Rn is a vector space.
Do you understand?
Do you understand?
Okay.
Okay.
Yes.
Yes.
So
one more example.
Now,
for example, I have R3. R3 is a vector space.
Yes or no?
Yes or no?
Yes, this
is the vector space.
Because
R3 is a set of all vectors with three dimensions
for every
vector. So we have vector u, we have 1, 2, 3, vector v maybe 2, 3, 4. Okay, they are all belong to vector space is R3.
So if I have
vector x with 1, 2, 3, 4.
How many elements? 4. So
that means x not belong to R3.
Do you understand?
Do you understand?
Okay.
Yeah.
Is it clear?
Is it clear?
Can you get to my point?
Can you get to my point?
Very easy.
Very easy, I think. Okay.
So
continue. We have a vector space of infinite sequence of real numbers, and here we have demonstration. Okay, you just remember we have a vector space of infinite sequences of real numbers. Okay, vector space of 2 and 2 matrices. Keep silence. Okay.
So here we have
n
rows
and n column, right? Because this one like a square matrix.
So we have the vector space of all matrices with 2 rows and 2 columns. Okay. Yeah. So this is demonstration. Okay. This is
so we have the vectors demonstration. Okay. This is SL number 1. This is SL number 6. So we have vector u with 4 element, right? Because this is the matrix. We have u1 1, u1 2, u2 1, u2 2, and we have vector v, v1 1, v1 2, v2 1, v2 2. Okay, this is okay. So when we verify SM number 1, we have u plus v. U plus v, you get this one plus this one, this one plus this one, this one, this one. Okay, so totally we also have 4 elements, right? So this belong to 2 and 2 matrices vector space.
Do
you understand? Okay.
So
now we have more practical example. For example, I say VGU is a vector space. Yeah. And all of you belong to VGUs. Yeah.
Okay.
Yeah.
That's right.
That's right. Yeah. Another example, I say ECE program is a vector space.
So all of you
belong to vector space,
right?
But for example, main program or maker program or the other programs are not belonging to the vector space. Understand? Yeah, very easy, right?
But why
we define vector space?
Why? Why we need
vector space?
Okay, because
we need the solution.
The solution
should be
in the vector space. So if
I would like to find out the best students of ECE program,
to the vector space
is ECE program. Okay,
I
we don't care about in text.
I say ECE
parameter vector space.
Okay, and then
I can. It's very easy for us, for me, to pick up the best ECE students.
But if
I say
VGUE
a vector space,
the space
the space is large,
the
the space is
So
wider,
I need more
time
to filter
to
out
filter out who is the best ECE students. Become more population,
Do you understand?
You understand? Vector space.
Yeah. So it depends
on your experience.
Okay, so
if you limit,
if we shorten
the vector space, maybe you cannot find a solution.
If the
vector space is very large, you need more time, maybe one day, 1 week, 1 month, 1 year to figure out who is the best ECE students, because vector space is large. Okay?
Yeah. Okay. For example,
I say Vietnam is a vector space. I would like to figure out the best ECE students.
I need to check
every university,
The whole
Vietnam, we have more than 150 universities. I need to double check who is and where is the best ECE students.
You understand?
You understand?
Yeah. Okay.
So if you go to the third year,
and
you follow automation technologies, you will see me another course which is smart system in automation, and then
we come back to
vector space. Okay, we apply vector space for optimization methods. Okay. Anyway, if SM1 and SM6 are satisfied, the other axioms, normally
I continue
to be satisfied. Okay.
Now
we have more general case. Now we have m rows and n columns. Okay, of course. Okay, we have a vector space of
m rows
and
columns.
Okay, not 2 and 2. Now we have more generally, m rows and n column matrices.
Right?
Okay.
And
we also have a vector space of real values function, and this is demonstrations. Okay.
Yes,
very easy. Okay, you can understand for yourself.
Okay,
and now we have a vector space of all polynomials of degree 2 or less. Okay.
We
have the polynomial bx is a0, a1x, a2x squared.
We
have qx,
another
polynomial function qx is b0, b1x, b2x squared.
Okay,
we double check with SM1, right? bx plus qx. You can get a0 plus b0, a1 plus a1, a2 plus b2, the same format with polynomial function. This is the simplification of SM1, and then we continue. We double check with SM6, and we say we have vector space of on polynomial. Okay. So yeah. We have some typical cases. Okay. Says that is not a vector space if
now
if we consider SM1, we have U plus V. This is R2, right?
It's R2.
It's R2. Vector space is R2.
Because every
vector will have 2 elements, so we know V is R2.
Okay, and
then we have U plus V. You can get U1 plus V1, and then U2 plus V2. Of course, this one belongs to R2, right? That's okay. But remember this one.
If you
define k times u is k u1 0. You define for yourself this one
because you
can define vector space for yourself. Okay, so now if we have k times u is k u1 0, and then for example we have vector u, c times vector u should belong to R2, right? And vector u is 2 and 4.
Okay,
so now we have k is 7, c or k. So 7 times vector u, you get what?
14
and
20,
28.
28. Okay.
Okay,
But
you define
SM6,
SM6. You define here
must be what?
must be what?
Must be what?
Must be what?
Must be 0.
Must be 0.
Right?
Right?
0. But here
0.
is.
But here is 28.
So if you
define
U1 plus
U1 plus U
with
plus
this,
with
and
this, and you define SM, you define scalar multiplication like this. So V is not a vector space.
Okay.
Okay.
V
is a vector space if what?
If
If K times UA,
KU1
and KU
U2.
right?
Right?
But here we define
KU2A
KU2A
0.
0. So this one is not vector space.
Do you understand?
Do you understand?
Good.
Good.
Okay.
And similarly, this one, the problem is here.
The problem is here.
Okay.
So U plus
V is UV.
when you double check.
Yeah, correct.
But if we have
K times U in U to the power of K, we check Asium what?
Is it correct?
Is it correct?
Let me see. We have
U is 1, right?
U
is 1.
UE1. And we have
case E2.
Okay, so we
have 2 times U is
EU, right?
1 to the power of 2, you get 1. Okay, correct.
This is correct.
But this one, UE 1
and
U is 1, and we have
like this,
like this.
We have 0 vector.
We have 0 vector is 1.
Okay, so
U plus 1 must be
U plus 1
must be
1 plus U.
1 times U, you get U. Okay.
Because
we define vector U is 1. 1 U, I mean U plus 0
is
1 times U, right? Because vector 0 is 1 times U is U. Okay? Correct.
Okay, how about
this one?
Now
we have U
and
vector U, we have U,
and
vector V, we have minus vector U.
Vector
V is 1 over U.
Okay.
So now we check vector U plus vector V.
You get U
times V.
Okay. So
U is here.
Then
And then
vector
V we have the element, only one element, 1 times U.
So U and U,
you get 1.
Okay. You get 1. Let me see.
Okay, a little bit complicated.
This is
vector space, right?
How can I explain
to you?
I mean,
every vectors we only have one element,
and
the element is real number.
It's
positive real number. This is special case, unusual vector space.
Okay, but you don't worry.
Because this is a typical case. So we seldom see
this case
in practice. Okay. Yeah.
For example,
this is the vector use, and we have the real numbers. Okay, the real number of vector use 1.
Anyway,
we have the vector space. That's the set of positive
real number.
It must be positive, because if negative is wrong. Okay. Yeah.
Show
The key
the key
slice is here.
Okay, we
Okay,
have
we
a
have
summary
a
of
summary of
vector
important
space.
vector spaces.
We have R.
We have R. This is vector space. R2 is a vector space. Blah blah Rn
Is a vector
is
space.
a vector space.
We have
We
Bn
have Bn is the vector space with
n degrees or
n
less.
degrees or less.
Okay. So
Okay.
we have
So we have
M and
M and
N
N
This
matrices.
is vector
This is
space.
a vector space.
Okay, and
Okay, and n rows and n
and
columns
an n
and
square
an n
matrix
square
is also
matrices is
vector
also
space.
vector space.
Okay, we have
Okay, we have
common
some
vector
common
space.
vector
For
spaces.
example,
For
R
example,
n.
R n.
Okay,
Okay, M m rows and column, M n row and n
Okay,
columns. Okay,
Bn.
Bn
Yeah, and
and
continuous function.
continuous function. C.
Continuous function
Continuous
with
function with
the
the
interval
interval AB,
or we have
or we
continuous
have continuous function
with minus
with minus
to
infinite
positive
to positive infinite. This is vector space.
common vector.
Common vector space.
Okay.
Okay.
Any questions so
Any
far?
questions so far?
Học toán dễ hả?
Học toán dễ hả?
Thấy dễ.
Vẫn thấy dễ vậy. Thấy gì đâu nào.
You understand?
Some students ask me about this one.
You know.
You know.
So
So for this one we define for yourself. Okay, we define for ourselves.
we say
We say u
u plus v
plus v
is u times
is
v.
u times v.
Okay.
Okay, and k times u is
u to the power
u to the power of k.
To
Okay, to remember this
the
is
set of
the set of positive real number. So we say vector u
u.
is 2.
This one belongs to
This
real
one belongs to real
right?
number set, right?
We have vector v
We
is
have vector v is a3. This belongs to real
right?
number set, right?
We have
So if we have u
plus v, that means u
that means u times v.
That means 2
That means 2
times
times 3 is 8.
belongs
6
to real
belongs to real number set.
Right?
Right?
Do you understand?
Do you understand?
And then we have
k times u.
So maybe
case is
some value,
some value, you know. Case is 2.
So we have 2
So we have 2 times u.
u to the power
u to the power of k. U is what?
2.
2.
2 to the power
2 to the power of 2 is 4 belongs to real number set.
So this is
so we have a vector space, right? A vector space to contain all positive real numbers.
Is it clear?
Is it clear?
Okay, but I mean
this is unusual vector space.
Okay.
Okay.
Yeah.
Yeah.
And then we
continue to demonstrate SM4, 5, 7.
4, 5,
4, 5, 7, 8, 9, 10. Okay. Yeah.
So you know
this is the zero vectors.
Yes, zero vector.
Yes, zero vector. And then we define zero vector is 1.
Okay, zero vector.
Zero vectors.
Because this is
positive real numbers.
You know?
Yeah. Yeah.
And then if
u is 2
plus
zero vectors, you can get what? 2
plus 1 you can get
3 belong to real numbers. Okay.
Just
we define the vector space. Remember when we define the vector space, we need to double check how many axioms. 10 axioms.
Okay. So if we
define the vector space like this, you are stupid.
You know?
So if we say, this is the vector space, and we say k times vector u is ku1 0, you are wrong.
Because
if we double check axiom 6,
k times
u must be what? ku1, u2. This is not 0. Okay.
So if we
have a wrong vector space, you cannot find the solution. Okay.
So for example,
we would like to figure out the best Vietnamese students.
But your
vector space is Germany. Oh my God, you are stupid.
You know,
wrong vector space.
like this,
like this,
like this
like
is
this
not
is not vector space.
okay.
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 So
So we have
for
another, for example,
the set
the
of
set
the
of the
integer
integer
is not
is
a vector
not a vector space,
right?
right?
One is integer.
One is integers.
One is integer.
One is integers.
But
when we double check SM6, we have C times U must belong to
integers.
integers.
Because we say a
Because we say a
set,
set, the vector space is the set of integers.
so
So
C
C
times
times vector U
should
should belong to integer.
But
But now we have
one
1 over this scalar times 1, you get 1 over this is non-integers.
right?
Right?
So
So the set of integers is not a vector space because SM6 is not satisfied.
Understand?
You understand?
Yeah.
Yeah.
Okay.
Okay.
Question so far?
Question so far?
Okay.
Okay. Yeah.
Continue.
Continue.
The
The set of
secondary
secondary polynomials
is not
is not a vector space.
Is that correct?
Is that correct?
Yes.
Yes.
Look.
Yeah. Look.
No.
Look.
We say
B and is
the
the vector space, right?
That means
B2 is a vector space because
every
bx we have what? We have a0 plus a1 x plus a2 x squared.
It could be 2.
It could be 2,
Right?
right? So if we have qx, we get b0 plus b1x plus b2x squared.
Okay?
Okay, so if we double check SM1, you have bx plus qx is what? A0 plus b0, a1 plus b1, and then a2 plus b2 x squared. You know the same format, right?
Okay?
Okay, so if we have c times qx,
that means
you can get c times b0 plus c times b1x plus c times b2x with the same format. So b2 is vector space. But now look,
we have
the polynomial, but we only consider what? The secondary.
The secondary
The secondary is here,
right?
right?
We cannot say
x or 1,
right? We just
have x squared.
Okay?
Okay?
So
now if we say bx like this and qx like this, okay? And then when we apply SM1, we have bx plus qx is what? A1 plus x. This one is not secondary. This one is the tertiary.
Right?
Right?
So
this one is, of course, so if we compare this one and this one,
they're different.
they're different.
That means
a set of secondary polynomials is not a vector space.
You understand?
You understand?
Yeah, we need to consider
less. Okay. That in the region here, we need to consider
the read
twos or less. Okay.
On
polynomial.
Okay,
so continue. Yeah, this one we discussed before, right?
This set
is not a vector space because C times x1, x2 must be equal to Cx1 and Cx2. We need to say Cx1 and Cx2 different from 0.
Okay, here
you know Cx2 is 0. Okay, so but this is not vector space. Okay.
Yeah. Enjoy. What is it?
Let me see. Let me remember.
Oh, I remember.
I remember. This one is the famous companies in Germany.
I
forgot German name, but this is the good company
in Hebron.
In Hebron.
Pfefferlux.
Okay, Hebron. In Hebron. Let me see there.
I will show you.
I will show you. Okay.
Cái tên gì? Cái tên gì? Phép phong blog.
Công ty gì? Fox. Maybe I says. Maybe you AI.
Here.
Here. Here.
Pepper.
Pepper. I don't know German. Okay.
Pepper.
Pepper.
Phúc.
Fox.
Uh,
I don't know. Okay, you know.
okay, yeah.
Okay, yeah. Very famous for our electronic sensors and automation device. Okay.
Yeah.
Yeah.
You said that R2 is not a vector space, summary opposite vector space is R2.
Where?
Where?
The second one.
R2
is a vector space.
R2.
R2.
But you need to
define C times X is C is X1, C X2, blah blah blah.
And then
CX1, blah blah CX2 must be different from 0. But now look this one we define this is 0.
we define this.
We define this is 0, right?
So this one
So
is
this one is not vector space.
opposite
Opposite are 2, but it is not vector space because you define scalar multiplication like this.
Other questions so
Other
far?
questions so far?
So
No questions.
Continue.
Continue. Okay.
Now we
come to session 2.
We
Discuss about subspaces
vector
of vector
We have
space.
vector
We have
space
vector space and we have the subspaces.
Okay.
Okay, of vector space.
Okay.
Okay.
For example,
I say ECE program
vector
is
space.
a vector space.
Okay. So
we have the space, your female group and male group. Okay, we have subspaces. Okay. Yeah.
So we
determine whether a set W
of
a vector space V is a subspace of V or not.
we have many
subsets, but you need to demonstrate a subset is a subspace. Okay, a subspace.
And
determine the subspace of R.
This is the key.
This is the key content of session 2.
Okay. Now we have definition.
Now we have definition. You have 3 minutes. Try to understand a definition first. Okay.
Not easy to understand.
Not easy to understand.
Fully understand.
Okay. I mean fully understand. Okay.
Okay,
Okay, so
in summary,
in summary, we can say
W
W
W
W
is
is
a
a
non-empty set,
non-empty subset,
okay, of vector
okay,
space
of
V,
vector space V,
and then
and
W
then
is a
W
subspace of V if
is
they have the
a
same
space of V
axioms. They have the
if
same
they have the
characteristics.
same
Okay,
axioms. They
so
have the
that means
same
if we have
characteristics.
U
Okay,
and V
so
and vector U plus vector
so
V
that's vector U plus vector V should
belong to vector space V.
belong
Then
to
if we
vector
have
space
vector
V.
U and
And
vector
then
V
if we
are
have
in
vector
W,
U and vector V are in
U plus
W,
V
U
must
plus
be
V
in W.
must be in W.
Okay, and blah, blah.
Okay,
That
and blah,
means
blah.
we should
That
have
means we should
the
have
same
the same
characteristics.
characteristics.
Okay.
Okay. For example, this one.
We have
W and V. Of course, V is a vector space.
okay,
Okay,
and
and W is a
right?
subset, right? It's a subset of V.
But when
But when we analyze
U,
U,
okay,
okay,
when
and when
we
we make a K times U, K times U is
outside of
outside of
right?
W, right? Outside of W.
Yeah. So
this one is not subspace.
Okay.
Okay.
Or
U plus V.
This is U and
This
V,
is U and V, right? U and V are in W, right?
But when we take
But when we take U plus V, you get
outside
of success W.
Okay.
Okay.
W
Yeah, so W is not subspace,
right?
right? Not subspace.
Because
subspace and vector space should have the same characteristics,
same
same axioms. Okay.
So
example.
We have
zero subspace.
Yes.
Yes.
We have zero
subspace. Yes.
Because
we have the subset W containing zero vectors.
Only zero.
Only zero
Right?
vectors, right?
Zero.
Only zero. And 0 plus 0 is 0.
And
K times 0 vector is 0.
This one belongs
to V, and this ones belong to subspace W. Okay? So we have zero subspace. Okay? We have lines
through
the origins are subspaces of R2 and R3.
Okay, this is
for example, here we have R3, right? We have X, Y,
three-dimensional space,
and we have the line
goes through
the origins.
This is a
a space.
Why we need
to
consider
origins?
We consider
origins because we need to consider zero vectors.
Right?
Yeah,
we consider
zero vectors. So if we have another line like this, okay, doesn't go through the origin. This one is not subspace
because
this one is not considering zero vectors.
Okay.
So any line goes through the origins will be subspaces
of R2
or R3.
Okay. Maybe Rn.
Rn. Okay, for Rn.
Right. So
if here we have vector U,
right?
Vector U belong to
vector space V.
Vector space V.
Is that correct?
Is that correct?
And we say
and we say V is maybe V is R3.
So vector u
So
belong
vector
to
U belong
R3.
to R3. Yes.
So if vector
So if
u
vector
belong
U
to
belong to W,
here,
here
vector u
vector U belong to
right?
W, right?
Okay. So
Okay.
if we
So
have
if
k
we have
times u
K times U
belong to vector
belong
v,
to vector V,
space v,
vector
right?
space V, right?
And k
And
times u
K
like
times
this
U like this
also belong
also
to
belong to W
and belong
and
to v.
belong to V.
So
So
they
they
have
have the same
characteristics,
characteristics,
right?
right?
So if we have
So
vector
if we
u
have vector
here
U here
and we have
and
vector
we
v
have vector V
should be here,
should be here,
right?
right?
So
So
u and
U
v
and V
belong to
belong
w,
to
right?
W, right?
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 So if we
So if we
plus
U
v
plus V
belong to
belong
w,
to W,
yeah,
yeah,
they are in
they
parallel.
are in parallel.
So if u
So
plus
if
v
U plus
also in
V
parallel,
also in parallel,
belong
to
to
belong to
w.
W.
Okay?
Okay?
And u plus
And U
v
plus V also belongs to
vector space v.
vector space V.
Okay?
Okay?
Do you understand what I mean?
Do you understand what I mean?
Okay.
Okay. Look.
Here we
Here we have X,
y
Y,
is x.
is X.
Okay?
Okay? That means we have vector space A R3.
So any vector,
So any vectors for
u,
vector U, we have U1,
two,
U2,
u3,
U3
belong
belong
to
to
R3.
R3.
Okay? So
Okay,
now
so now we have the curve with the line
go through this one.
goes through this one.
This a
This is
First
success.
of all, we say
First of all, we say this one is success, right? So now we need to demonstrate axioms theory. We have vector U plus vector V belong to W,
right? And
right? And see how vector U should belong to W. And U plus V belong to vector V. C times U belong to vector space V.
Okay? So,
Okay, so if I have vector U here,
so vector u belongs
so vector U belongs to success W, right?
and vector u say
And vector U say also belong to V, right? Sorry.
right?
Right?
Yes.
Yes.
Okay. So
Okay. So now we have vector V like this.
vector v here.
Vector V here.
So
So belong to
w and
W and V also.
do you read me?
Do you read me?
And now
And now
we take u
U
plus v.
plus V.
You get this one.
You get this one?
Belong to
Belong to
w.
W.
Also belong
Also belong to V. No?
v.
We say R3.
Okay.
Okay?
And if we have
And if we have K
u
times U,
okay,
K times U like this, case is negative. K times U
also
also
belong to
belong to
that
set W's and
okay.
V. Okay?
They have the same.
They have the same characteristics, so we say W is a space of. Understand?
So now we have.
So now we have the general
observation.
Any lines, right?
Itself
Any surface
go
through the origin.
They will be
Subspaces.
okay.
Okay? Yeah.
Any questions so far?
Any questions so far? Okay.
How about this one?
How about this one?
Blends.
Prove the origins are subspaces of R3.
That's right.
That's right?
Yes, of course.
Yes, of course. This is demonstrations.
The blend.
This is the blend, the blend.
Okay.
Okay.
Yeah. So now,
the summary.
If we have
vector space
R2,
so we have the subspace
zero, right?
Yeah, we discussed before. Zero subspace. Zero subspace.
Okay.
Okay. Lies
through the origin.
through the origins.
As
As
ECE itself.
ECE itself.
ECE itself.
ECE itself.
Okay.
Okay.
Now,
if we have vector space AR3,
so we have
zero space itself
that lies through the origin.
The
blends
the
origin.
through the origins.
Why?
Origins.
Because
the vector space we have 3 dimensions. So if we reduce 1 dimension, you get
right?
land. Right?
So if reduce
2 dimension, you get lines.
Okay. So now, if we have
this is R4.
So we have zero
vector space,
lines,
R3,
and R4.
and R4.
Yes.
This is R2.
This one is R1.
Okay,
you can say that.
Yeah, you can say that. That's okay.
Okay.
Yeah.
So
look.
The
subset of R2s that is not a space. Why? Actually, we have the constraint. With the constraint. Of course, we have a blend.
But we
only consider one. We only consider x is
higher than equal to
0. So that means we only consider this one.
And y
is
higher than equal to 0.
So that means we only consider
the
first quadrant.
This is stupid
because if we have negative,
this is
outside of
the
subset, right?
So
here we cannot say
the space
because we have limitation of x and y.
Okay. Yeah. So if
we don't have limitation, that's okay. This is a space.
But if we
limit,
this is not a space. Okay. Yeah. For example,
ECE's program is a vector space.
Okay. I say
I would like to figure out the best ECE student, and I give the limit of age.
Not a space. Right? 20 years old,
we also study ECE.
50 years old,
we also study
ECE.
If
we give the limit of
age, so limits of age is one of dimension.
The base of ECE
students belong to what? Age level,
family,
educational backgrounds, citizens, blah blah blah. Is that right?
Vector space.
Right?
I said
ECE program
is a vector space. I would like to
figure out who's is the best
ECE
student.
I don't know.
I don't care about your family, your citizens. Okay. Your
Mẹ gì đó.
Anyway,
this is
a function. Okay.
This is a function.
This one is f.
This one is F.
This one is f. Right?
How many dimensions
we have? I don't know. It depends on your definition. Right? So if I say vector space here is R3,
that means
the best students should have three elements.
The first
element may be 8 levels.
The second
element may be
what?
Please help me.
Maybe
citizens.
Right?
Maybe it's Vietnamese. Maybe it's
Where you from?
Where you from?
I'm from
Okay. And which one? Here, try to get more dimension. Gender. Maybe gender is not good. No? Yeah.
Normally
we cannot say it's a gender because okay. But yeah, wearing glasses. Good. Okay. So if we have more dimension, maybe you cannot figure out the best is the student, to try to
think about the vector space.
You have maybe
R1 will be better.
Okay.
Yeah.
You understand? Yeah. Normally is ECE is male students studies back. It's better than female research. Also. So we have some space, right? We have some space. Okay. So continue.
We have
some spaces of
n rows
and column matrices.
Okay. So
what are the spaces of n rows and n columns?
We have
symmetric matrices, right?
Do you know symmetric
symmetric matrices?
Okay.
We have upper or lower triangular matrices.
Diagonal
matrices. Okay. They are on
subspace
of matrix. Okay.
This one
just a typical case. Okay. For your reference, we talk about invertible. Okay.
So
just remember the set
matrices
of singulars.
Okay.
Matrices A not a subspace
and
of m rows and n column.
We also have
the theorem of intersection of two subspaces.
The intersection
of two subspaces is also subspace.
For example,
we have the subspace W, we have the subspace V, so the intersection between
V and
W is also subspace. Okay. Yeah.
Do you
understand?
For example,
here we have another subspace. We have another subspace. We have another line
like this.
Okay.
So
we have zero, right?
Zero
A. The intersection between this subspace and this subspace. So zero is also subspace. But actually we don't need it. Okay. We know zero is our subspace. Okay. Then
or if we
consider this one, that's okay. we consider the line, and then we consider a plane.
Okay, a plane.
A plane containing
a plane, right?
a plane, right?
And this is
line.
line.
So we have
The intersection.
the intersection in this one.
More.
Okay, more meaning.
Okay,
If we consider intersection between one line and another line, because we only have common one is zero factors.
Okay, so
What is it?
type break.
Type break.
Type break 10 minutes.
Type break 10 minutes. Okay.